This is the fourth and final section of chapter 5, and this section is about using large sample results for an unknown population. Now, there are some cases in which we do not know the population standard deviation. Now, in those cases, we can use the central limit theorem and the sample variance, and we can use an unbiased estimator to calculate the sample variance or unbiased estimator for the population variance to obtain the following results. Now, the following results hold when n is large, when we've had a large sample, we've used a large sample. So first result, if the population is normally distributed or assumed to be normally distributed, then if we standardize the sample mean, then that will be approximately a normal distribution, a standardized normal distribution. Because we know that the sample means will be normally distributed, and if we standardize that, then it should be approximately a normal distribution that's standardized. Now, if the population is not normally distributed, so we know that we've got a population, it's not a normally distributed population, and we assume that our sample standard deviation is approximately the population standard deviation, then the same results hold. That if we standardize our sample means, then we will have a normal distribution that's standardized, a mean of 0 and a variance of 1 squared. Example 13. As part of a study of the health of young school children, a random sample of 220 children from school A and a second independent random sample of 180 children from area B were weighed. The results are given in the table below. So in the table we've got n, the sample size is, we've got the sample mean, and we've got the sample variance for both areas B or A and B. Part A, test at the 5% significance level or level of significance whether there is evidence of a difference between the mean weight of the children in the two areas. State your hypothesis clearly. So we have our formula up here. Start with H0 and H1. H0, that the mean in area A is the same as area B, and because we're looking for a difference, H1, the mean in area A is different to the mean of area B. Okay, so here's my calculation to work out my test statistic Z, and that's minus 0.20499. Here's my little normal distribution curve to help me out. I know that critical value is 1.96 minus 1.96. So that means that my value of Z here is in the critical region, because minus 0.20499 is in critical region. I could say that it's less than negative 1.96. I'll write that out instead, so I could write this is less than that. So what do we conclude? We are going to reject H0. So by rejecting H0, there is evidence of a difference in the mean weights. Okay, part B. State an assumption you have made in carrying out this test. Well, notice that we have used the sample standard deviation on a sample variance here, and the calculation requires the population variance. Now what we've done is we've assumed that the population variance is approximately our sample variance for areas A and B. Now this is a valid assumption to make Since n is large, we've got large values of n, a large sort of sample size for both areas. And then lastly, part C, explain the significance of the central limit theorem to this test. Now, the central limit theorem allows us to assume that the sample means are normally distributed. That's what allowed us to do this hypothesis here, because we assumed the sample means were normally distributed, even if the populations are not normally distributed. We're not told that the populations are normally distributed, and we can do that because n is large. So you should now be able to do exercise 5C on pages 134, even 133 to 134 of the textbook.